All right. Good evening, everyone. We are back again with Dan Does Today. Tonight, we are moving on to sort of a new series of videos. We're not looking at a specific library per se to learn what it is. We're going to do line by line. We're going to walk through an existing tutorial line by line and hopefully understand every single one, what's going on. This was by viewer request, so this one goes out to Fiona. Thank you very much for this suggestion. And tonight, we are going to be looking at one of the TensorFlow examples. For those of you who are TensorFlow fans, we are back on that. We'll see how long we're at that for a while. It's certainly one of the more popular in terms of growth machine learning libraries out there. So as I said, we're looking at fully connected feed.py. This is an example that walks through the MNIST image classification dataset. So you should be familiar with that. If you're not, that's okay. This will also introduce you to that. You can go to their GitHub site and download it. I actually poked around on the main TensorFlow webpage, just trying to see, oh, how do I get to this? And I didn't actually find a link, so I felt kind of silly. But if you go to GitHub, TensorFlow, TensorFlow, examples, tutorials, MNIST, you'll see it right there. Looks like 4 people have contributed to this. So I've already downloaded that. I've got it over here on the right. And let's just start walking into that. Let me load up Python first. All right. So of course, this file is copyrighted by Google. That's just a big, nice license warning here at the front. Without warranties or conditions of any kind. I'm not going to go through line by line the Apache license. If you want to do that, I don't know what you're into, man. Okay. Let's jump right into it here then. So from __ future, this is just if you're using Python 2, this will let you switch to using certain Python 3 things. So absolute import, I actually don't remember exactly how that works. I believe that's if you're doing a from dot import something. The other thing with this, I looked at this file ahead of time, but I didn't excruciatingly plan out what it does. So let's just look at that. Let's be excruciating detail here. Python absolute import. Multi-line and absolute and relative imports. Make sure we understand what's going on. Long import statements can be difficult to write. Import can be ambiguous in invasive packages. Yada yada yada. You must enable new absolute import behavior. You may use relative import statement. Python 2.6, any import statement. All right, so this is just if you have really old Python, you should be using absolute import. If you're using Python 3, don't worry about it. All right, next line. Look at it. We've already finished one line. That only took a handful of seconds. We're so good at this. Okay, next line. From future import division. This is for Python 2 versus Python 3 division. In Python 3, if I say 2 divided by 3, I get 2/3, thereabouts. In Python 2, I would get 0, which the equivalent statement in Python 3 is //. By saying from future import division, you say, hey, do it the Python 3 way. Finally, one last fancy import, from future import print function. In Python 3, print is just a function like anything else. Most importantly, that how this affects people is you have to use parentheses when you do print. You can't just say print4. It will yell at you. This upsets a lot of people. I actually like this. I don't want things to be special keywords unless they really need to be special keywords. I believe it also means that you can do print4 and you can say file equals foobar or whatever, and it'll print to that file. Let's see how that works actually. File, a file-like object. Oh, you have to open the file already. So with file, with open foobar as f, you could say print foobaz file equals f, for example. And I should end my strings. There we go. And I'm in IPython, so I can use basic shell commands, so I can cat foobar and see that it's filled with toBaz right there. I believe I can also remove foobar. There we go. So that's what these are just setting up if you're using Python 2 to give you some nice Python 3 things. Import time. Time is a module in Python for doing time-based arithmetic. Most commonly used with time.now, maybe not time.now. I lied. Time.time. That's how you get the current time. In epochs, I believe. Or not in epochs, in second sense, like January 1st, 1970. Let's see how we can do that. String that. I always forget this. This is how to parse a string. No. Time dot string f time. Yeah, I want to format the time. Right. Convert a time tuple to a string, but time dot time. Turn to current time in seconds since the epoch. Yes. So if you're timing things in Python, and for example, if I say a equals time dot time, and then sometime later I say b equals time dot time, I can see how long was between those two things. And here is 4.32 seconds. So for simple timing operations, that's very nice. Okay, this line. From 6.moves, import xrange. So 6 is sort of a compatibility module between Python 2 and Python 3, because 6 has 2 and 3 as factors. So that's why they named it 6. So you might recall, if you're a Python 2 user, xrange is the way to get a range of values from 0 to n, say, but not get an iterator of those values, but not actually create the list. Whereas in Python 3, they got rid of xrange and just said, nope, we're just using range to do that. If you want the list of that thing, you need to call list. So for example, if I say range 10, that's some range object, and I say a of that, and I was like, all right, well, what's a of 0? Oh, I can do that? I didn't know I could do that. Huh. Point being, a is some range object. If you want the actual list, you need to call list on it. Whereas if I try to say xrange of 10, it will yell at me. So this is, if you have Python 3, really, make sure that you have xrange, because they use xrange in this. You could just change all the xranges to range in this file, and it would work just the same. So, but we'll run that line, that's fine. Now we can say xrange 10, and I will learn that xrange 10 probably equals range 10. Yep, same thing in Python 3. That's okay. All right, here's a moneymaker. Import TensorFlow as TF. That should be self-explanatory. This is the standard way to start using TensorFlow. As TF just means we can refer to things in this module with TF dot whatever. There's a lot of things there. So it just saves you typing. Whether you're working interactively or you're typing in an editor, same thing. Okay, now we're getting to the actual MNIST part. TensorFlow.examples.tutorial.mnist import input data. So they are reading their data in a really particular way in this problem. Pro tip, if you're in IPython, double question mark shows you the source code if possible. Something I love. Not always helpful, because sometimes whatever you're looking for just comes from something else, as is the case here. How can I even get input data if it's not a thing here? That's weird. Anyway, input data is how they're actually going to be reading in their data here. Let's see if we can just, I believe they talk about it in this, the code is on fire, the code. Yeah, here's input data. I said here's input data, there's nothing helpful here. It's hidden in another file. This read datasets must be the real. TensorFlow.contrib.learn. Oh my gosh. All right, let's go find that. TensorFlow contrib learn Python learn. Oh, that's the skflow or scikit-flow, I believe, was in there. Contrib learn Python learn datasets. Data? No, went too far. Trainer. Well, I lost track of it. Find it again. Contrib learn Python learn datasets mnist. Okay, so I didn't go too far. Datasets mnist. Jeez. I'll just define the actual data. Right, they're doing this business. Okay. So this is the same as before, just handling if you're in Python 2. gzip will need to decompress objects. OS is to make certain command line calls. Temp file is to have a small file on the file system for Python to read and write to that will clean up after itself. URL-lib is how you open a web page. That's how we're going to download the data. Maybe download, which is going to check if we have the data. And if we don't, it will download it for us. This is where the MNIST dataset lives. Jan LeCun's website. I apologize if I'm pronouncing his name incorrectly. All right, this is how we read in the data. The byte stream, I assume, is going to be an open file handle. Byte stream. Yeah, here we go. We'll get to this read 32 in a second. The extract images is how this really works. So you're passing in a certain file name, and they say extract the images into a 4-dimensional uint8 numpy array. So index, which image we're looking at, what row are we looking at, what column are we looking at, and the depth, which channel are we looking at. There should only be one channel in this. It's red, green, blue, but this is just black and white. This tf.g file, so TensorFlow is a thing to open up gzipped files, compressed files in this way. And it works just like the regular Python open. You say tf.gfile.open, file name. We're reading binary as f, comma, gzip.gzip file. File object equals f. Interesting that you can do this in this way. With this as, oh, so this returns two file handles. Or two file handle-like objects, I guess. So as f, and you can pass f in right here. Oh, that's crazy. I didn't know you could do this in Python. As byte stream. So basically, you're getting byte stream as the decompressed file, and you do this read 32 thing on it. What does that do? That uses numpy, a library in Python for doing numerical computations on arrays and other lots of nice things. And you're saying, hey, read this file that's binary packed, 32 bits at a time. And it says, read that, but swap around the byte order. And this tells you whether it's essentially big or little endian. And I need to remember now which one is which with that. I believe it points in the direction of the least significant bit. Numpy, little endian, byte swapping, byte order. Here we go. Nope, I was wrong. Okay, so pointing in that direction means big endian. There we go. Otherwise, you're going to get, all your values are going to be really screwed up. If you're paranoid about keeping track of these things for some data set that you have, you can always store things using numpy.save and numpy.load. And that's sort of endian agnostic because of how extra information it encodes in the save file. And those can be compressed too. Or use something like HDF5, high density format. Okay, they're opening up this file. They're saying, hey, figure out this information. They're calling it magic. And if magic isn't this special number, if it's not the right kind of file, in other words, then say, there's something really wrong with this file. You read the, oh, sorry. In this function, read32, just reads a single integer, 32 bits. And you're saying the next 32-bit value says how many images are in this data file. The next one says how many rows are in each image, how many columns are in each image. And then you simply read all those images. And you're using bytestream.read here. So you're no longer calling this read32 business. You're just literally calling, hey, read number of rows times number of columns times number of images. And yes, you're reading those as 32, guys? Just as, I guess just as bytes, because it's a byte stream. So this is how many bytes you're working on. And then you're saying using numpy to say, hey, use this from buffer command. A buffer is just a byte stream in like Python 3, which is sort of like a string, where it just holds data. It holds a bunch of 8-bit values. And it says, hey, put this in one big long chunk called data, and then reshape is going to say, hey, change around the shape of that from a one-dimensional array to this 4-dimensional array. So you've got this many images, this many rows, this many columns, and one channel. And give that back to me. Let's continue. We'll get to what these other functions do when we get there. Let's for now just import that, input data. Likewise, let's just import MNIST. Oh. Okay. What are we doing now? Basic model parameters as external flags. Flags.tf.app. So tf.app is not something I've used. Implementation of the flags interface. All right. Generic entry point script. Yeah, that's cute. So I got flags lowercase and I have flags uppercase. Oh, because it's flags. What is this? Global container and accessor for flags and their values. Okay, so this flags interface here is a way to set a lot of the parameters in the model we're going to build. So for example, you can define a very particular value in flags called the learning underscore rate. That's going to have value of 0.01, and you can leave a little note to yourself about what it is, initial learning rate. Likewise, you can say define integer, number of steps. So that I believe this is like how many epochs we're willing to go through, number of steps to run trainer. I believe that's correct. Hidden 1, this is just how many neurons are on our first hidden layer, where first is sort of closest to the input. So we've got 128 neurons, number of units in hidden layer 1. Hidden 2 has only 38 neurons, and so this one, hidden 2, receives as input the output of hidden 1. So each neuron is receiving 128 inputs. All right, batch size. This says 100. Woo! Excuse me. The batch size says how many images we will train on at once. So if the batch size is 1, you'll look at that image, you'll run it through the neural net, and you will compute the gradients and determine, okay, I need to update all my values by this much. If the batch size is 100, you run 100 images through your neural net and compute one gradient based on all of those and sort of averaging. I'm hand waving the averaging part. Let's see how that goes. So typically you might batch size like 32 or something if you've got a GPU that can do all that many things at once in a way. Here we're doing 100. I'm not 100% sure why it's 100. It says must divide evenly in the dataset size. Okay, define string. Train-dir data. Directory to put the training data. Oh gosh. Hang on. I might want to change that. So it's going to download the data for us. And that's where it's going to put it. But I've downloaded this data before. Data. Maybe I haven't. No, I know I've downloaded MNIST before. Whatever, okay. You will then download things to training directory data. If you want fake data, for whatever reason you don't have access to the internet, say, you can just use fake data and it will generate some image-looking things. And your weights probably won't make any sense, but that's okay. You'll be able to see if the model even runs. Overall, I'm really not a super big fan of this fully connected thing as a tutorial. The page on the main TensorFlow web page is, I like that a lot better. Just like the MNIST for ML beginners or the deep MNIST for expert. This walks through like a lot of the math and shows you the code. Although some of the related tutorials show you less of the code, which I find irritating. So there's really no winning. Okay, we've got placeholder inputs. What does this function do? They say generate placeholder variables to represent the input tensors. Placeholders are used as inputs by the rest of the model building code. Will be fed from downloaded data in the run loop below. Batch size, how many batches are you running? Returns, images placeholder, and labels placeholder. Okay. So images placeholder, so when you create make sure I state this correctly. When you want a value in your TensorFlow graph, you typically use either a tf.constant, a tf.constant, say z equals tf.constant 0 maybe. Someone says, fully feed connect is part of TensorFlow Mechanics 101. Okay, well, that's interesting. That's good to know. That's how you can get there. Go to chat if you're wondering. All right. So you can make a constant or you can make a variable. B equals tf dot variable. So variable is something that's going to change. And how does that self, initial value, yada, 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 yada. Do I even need to pass in a shape? I might need to pass in a shape. Initial value must be specified. Okay, well that's 0. Z and B. Oh, Z and B. There we go. So variables are values that are going to change during your computation. Typically these things are your weights. Constants are things that are not going to change. They are constant. So what the heck is tf.placeholder? Tf.placeholder is a constant, but it's one that you are going to provide the value for at a later time. So for example, you typically use the tf.placeholder for your input data, hence your images placeholder. And by using placeholder, TensorFlow will yell at you if you don't supply a value to it when you actually train your network. And we'll get to that bit in a second here. And here we're declaring the data type of this data. So it's 32-bit float, so that's 32-bit rational numbers, decimal numbers, you can think of them. It's known as single precision. And the shape is whatever we said the batch size was. In this case, it's an input to this function. Comma, geez, hang on, there we go. We'll walk through this. Actually, I'm going to make this a little smaller. That's too small. Screw it. MNIST.ImagePixels. So what is MNIST.ImagePixels? That's the question. MNIST.ImagePixels 784. So in this case, even though it's an image that's 28 by 28, we are pretending it is just batch size, comma, 784. That is, we are throwing out the structural information of our input features because we're just going to do a fully connected, dense hidden network, not a convolutional model of any kind. Okay, and again, images is going to be the actual image values, the pixel intensity values at every position. Labels placeholder is going to hold what is the actual label of this image that we're looking at. What digit it is. Is it a 0? Is it a 1? Is it a whatever? And that's why it's tf.int32. You could also use, for example, tf.int8, whatever. I'm a little surprised this isn't already in one-hot format. Oh no, yeah, no, I'm a little surprised at that. We'll get to one-hot format in a second. And a shape is of course batch size, because you've got that many images you need to deal with. And this function just returns those things. So let's run that function. Let's skip all that stuff. There we go. I can't do that? Okay. I missed a line here. There we go. Let's turn off auto indentation. Okay. Fill feed dict. Fills the feed dict for training the given step. You give it a data set. You give it an images placeholder, probably, and a labels placeholder. Just a guess. Images placeholder, hey, what do you know? Set of images and labels from input data.read datasets. Images feed, labels feed, dataset.next batch. Okay, so dataset. Let's go back to this fully feed connected. No, let's go back to mnist. This is almost certainly an instance of class dataset. Batch, next batch. Here we go. So we're going to open up a dataset object that we'll get into later what exactly that is. For now, don't worry about it. Next batch is how we just grab the next batch size samples, so next 100 samples, say. And I believe it probably does the right thing. If you're using fake data, this is where it generates it. It says, hey, you've got 784 ones. Very, very, very nice and fake there. And they're all zeros, apparently. This is the one-hot format, where you put a 1 in whatever position represents that digit, and 0 everywhere else, so you'll have a 10-long vector or list here. Otherwise, you just put in the actual value. And it returns that actual fake image for however many are in the batch size. Okay, but if it's not, start equals self.index in epoch, self equals self.index in epoch plus equals batch size. So right, where are we right now in all of our data set? Grab the start, update where we are in our data set with the batch size because we're grabbing the next 100 or say. And then if we're beyond the end of the data set, index in epoch where we are right now, beyond num examples, that means yes, we're finished with the epoch. We don't have to do any more training after this. So we say, hey, we did one more epoch. That's great. So after doing an epoch, we shuffle the data around to make sure we're not just looking at it in the same order every time. So numpy.arange just generates the numbers 0 through n-1. So we get a big long list of the indices into our examples here. Numpy.random.shuffle just randomizes the order of those numbers. So get a random listing of the numbers 0 through n-1. And then we grab those numbers. Self.images is an array here. And when you input a list into a numpy array, let me show you. In fact, a equals numpy.arange 10. Import numpy as np. So that's A. A is the number 0 through 9, because we put in 10. So you get n-1. So you get 10 things, right? And if I say, for example, numpy.random.shuffle A, now A is in a wacky different order, right? And if I want to say B equals numpy.random.random 10. So B is a random integer, or a random array of 10 things. And look at 0.49 comes first here, then 0.45, whatever. But if you say B comma A, with A in this order, we're going to get those entries of B in the new order specified by A. So we'll get the fourth one first. So 0, 1, 2, 3, 4. So we're going to start off with 0.03. Boom, look at that, 0.03 first. It's a miracle. So that's what this does. This just shuffles your data, your images, and you shuffle your labels the same way. Then you start a new epoch. You update where you are in the epoch, of course. As you say, hey, do the batch size, and then you super double check. You say, make sure that I have at least as many examples as my batch size is large. Okay, then you continue. You set the end to be wherever you're right, because you updated index and epoch value, and you just return those images. So essentially, what all this is doing is just grabbing batch size images at a time and sending them to your data set. and after every epoch, shuffling the order of the data. Question from the audience. Is there a standard way to create training batches? I run out of RAM when appending to a NumPy array. So if you're running out of RAM, one thing you can do is just only read from the file system into a NumPy array a batch when you need it. I can get into that more later if we have time, but don't read in all the data at once. Just read it in when you need it. So depending on your data set, this might mean keeping all of your examples in different files, or keeping the file handle open and reading from it as is needed. In general, this is hitting your file system a lot more. If your epochs are very quick, this means you're going to be pounding your file system, which will slow things down. As I said, if you want me to cover that further, make sure to leave a comment in the video so I don't forget. Where were we? We were pressing forward. Fill, feed, dict. Okay. So that was all about next batch of batch size and fake data, which is, recall, fake data is false. Flags.batch size. Batch size. Doesn't work. Presumably, that's because this isn't running as an app, and this flags business only works in an app, which we're going to find out how well that works in an interactive session real quick. So let's just run this stuff. That's good. All right, feed dict. This is what we're outputting. So we're saying images PL. That's what we're telling TensorFlow, the thing we're filling in, this node in the graph, which is really going to be this thing, this placeholder that we defined. Hey, it says put in this images feed thing, which is just the next n images, the next 100 images or whatever. And do the same for the labels. And because they're placeholders, if you don't send those things to TensorFlow, it will yell at you. So let's do that. Return feed dict, return outside function. I disagree. I don't think that was a return outside function at all. Return feed dict. Son of a gun. Getting burned by this 2. Return feed dict. There we go. Okay. Now we're getting into the real model here. Slow going, but we're being excruciatingly meticulous in doing this. So this is a level of detail I do not normally go into when I'm doing a model. I'll try to explain things, but if this is just being super crazy, if this is what it takes to make sure we understand it, that can be good. And I have benefited myself from going through in such detail for other things. Random aside, I spent a summer doing research on material science and geology once, and I was staring at this certain equation of material flow under heavy temperature and heavy pressure and high temperature. And there's so many different things going on. I just went through and I said, okay, what's this variable? What does it do? Where does it come from? And sometimes that means you have to dig inside into a function, into another. That variable comes from another formula. So go to that formula, figure out what it does, look up the references. It can take a lot of time and it fills up a lot of pieces of paper. But at the end of it, it can often help you really understand what's going on. And in this case, doing the research, I discovered a flaw in one of the formulas that helped us fix up a lot of our research. And I happened to be an undergrad there, just doing some summer research, and one of the grad students was thankful that corrected something before she was too many years into a PhD and found out that it was slightly wrong the whole time. Anyway, let's do eval. You pass in a TensorFlow session. You pass in eval correct. What is eval correct? The tensor that returns the number of correct predictions. So how many things did we get right in our prediction? I would have thought we wanted to return the percent correct or something. Images placeholder. Of course, this is just going to be the placeholder variable that we generate somewhere else in the earlier function. Same with labels placeholder. Data set. This is the actual data set that we've read in. And we're going to use this read datasets function. Let's take a quick look at that. Read datasets. Really? Oh, it's in input data, not in this one. Not even in this file. It's in data? No? It is in this file, right? Read datasets. Oh, there we go. Okay. So where's your training data? Is your data fake? Are you making fake data? Do you want it in one hot format? And what's the data type? And here we're saying it's TensorFlow.float32, 32 bits. They're using TF.float32. You often see that people use NumPy, NP.float32. I imagine, so they're both 32-bit floats. They're encoded the same way, I'm 99% sure. It's just a matter of how they're represented in Python as a Python object. So it's TensorFlow, use the TF. They instantiate an empty class here. That's what the pass is for. But we're going to add a whole bunch of attributes to it. We say let's make a new instance of the class, datasets. If we're doing fake data, we generate some of that fake data, def fake. We make an empty dataset of dataset this fake data equals true one. How? But this is data set versus data sets. Data set is already been defined up here, which we went through in certain level of detail. Oh, hang on. Okay, these are the file names from Jan LeCun. This is how he labels his files. That I've got training images in unsigned bytes, similarly with labels, and he's got a server testing set. And the validation data set is 5,000 long. And now they've got a series of things called local file and train images. So local file maybe downloads it, checks if it's there, and if it's not, it downloads it. It says, hey, look for this file in this location. If it's not there, go grab it here. And extract images. There's something we haven't looked at yet, or did we? I thought we did. We did. That was this business here. So it generates the NumPy array of, the NumPy array of all your images. You might just save off that if you're working on your own data set. I like to work with NumPy arrays and just save them off. Okay. And then you do the same thing for the labels, for the testing images, for the testing labels. And what do they do here? He's got test images. Oh, these are the testing set images. And then the validation set, right? So you've got training, validation, and testing. So you train on the training data set, of course. That's how you set your weights. You use the validation data set to sort of decide what type of model you want. How many layers, how many nodes in each layer, what the learning rate is, for tuning your hyperparameters. And then use the testing data set to actually estimate what the final error rate of your model is. So after you sort of finish your model and you say, okay, this model's good, I like it, based on the validation data set and the training data set, then you run it on the testing data set and you see how good you really did. And that's sort of the final estimate of how good your model is. Okay, yes, and this colon validation size just says, hey, grab the first 5,000, those are your validation set. This, of course, says, hey, start at the 5,000th guy and go to the end. That's your training data set. I guess in this case, the data set is in sort of a random order. Like, because I thought this training is like 60,000 images, maybe it's 65,000. But if, for example, all your 0 digits came first, you'd be skipping a lot of them if you just took the first 5,000 in your validation set. That would be kind of bad. That your training data set hardly ever gets to see a 0, and then the validation set is all zeros, you're going to have a terrible model. So, but maybe they know ahead of time that it's been randomized, and I believe that is the case, actually. Okay, datasets.train. This is just saying this is the data set we're going to use for training, this is the data set we're going to use for validation, This is a data set we're going to use for testing. All right, let's get to the actual training here, huh? We're only halfway through this file, and it's already 6:40. Oh my goodness, this is taking longer than I thought. Maybe there's more to this. So this is do eval. True count counts the number of correct predictions. Yes. So this is just keeping track how many guys we got right in our labeling. Something is generally considered correct in the MNIST model if the predicted class probability is the highest one. If the probability for the correct class is the highest probability of all the predicted probabilities. So it could be 20% and the other ones are all pretty low. And, well, no, I guess if it's 20%, it's not the highest. All right, if it's 25% and the rest of the probability is evenly distributed, it's still the correct result, even though the model's really not that confident. Steps per epoch. Flags.batch size. Dataset.numExamples. Oh, divided by flags.batch size. Interesting. Oh, so this is just letting us know how many batches are we blitzing through in one epoch. We're just computing that ahead of time. NumExamples, we're going through, and I don't know why we don't just, we don't just pull NumExamples here, because note the integer division here. So we're going to end up with potentially fewer if NumExamples is not evenly divided by batch size. I thought they rigged that, so that is the case though. Whatever. For step in X range, steps per epoch, right? So we're going to say, hey, generate the feed dict. So grab those placeholder values from the TensorFlow graph, stuff in the data set of the next batch, do this many times, and when we do that, run our eval correct. Eval correct, eval correct is a node. I see. I am misunderstood. Eval correct isn't just a number, it's a node. It's a TensorFlow node. So this is the computation that actually computes the accuracy of your model. And of course you have to pass in your feed dict, pass in your current data set. And you're walking through all the steps of your data. And so of course your precision, how many are truly correct versus how many did you run through. As opposed to recall, and you can do the F1 score. Well, I don't think in this case we've got. That may not make any sense. I'd have to think about that. I'm used to thinking about binary classification in that realm. There we go. So now we've got do eval. Run training. So do eval is all about evaluating the accuracy of your data, but not training anything, because you're running just the eval correct node. Train MNIST for a number of steps. Perfect. Data sets. So yes, this is where we do input data.read data sets. Where is the data supposed to live? And flags.fake data, are we making fake data? Generally no. Okay. And here, with tf.graph.as default, that's actually new to me. Tell TensorFlow the model we built into the default graph. So that's like the default session, I think. tf.graph.as defaults. I save off everything to A, just because I want a helper for context manager decorator. Not helpful. So I believe this is a scoping issue. So we're going to define a couple nodes like eval correct here within a particular scope in TensorFlow. So make sure we don't squash other things. Because this is all in functions, that can be important. Okay, so you grab your placeholders, the nodes that we're going to put our data into, placeholder inputs, this many, batch size, logits, MNIST.inference. Does this build a graph that computes predictions from the inference model? So MNIST.inference, I believe, is the actual model. Really? Datasets learn. Datasets, models, trainer, learn, no. MNIST.inference. Build the MNIST model up to where it may be used for inference. Yeah, that's cute. Yes. So this is what's hiding the actual model, which is irritating. The actual TensorFlow model here. That's what this is doing. This MNIST.inference. It's saying, what are your inputs? Images. I don't need the input labels to run them through the model. How many nodes in the first hidden layer? How many nodes in the second hidden layer? So this is sort of an skFlow like specification where you have sort of one line neural net. And they walk through that here on the left. And I'm not going to go into that, but let's just note that they're initializing their variables with truncated normal. They are using rel_u as the activation function. I don't think there's anything else too special. And it's outputting the logits, the final output of the class. These are soft, yeah, softmax is their final output. So logistic regression on the end of it, which is standard. Then you can compute the loss. The loss is just how wrong we are. I believe for typical like categorical cross entropy, you just look at what is the probability of us being correct, and the closer to the 1 that is, the better. You sort of don't care what the distribution among the other non-correct answers is, which you can argue if that's right or not. Add the graph to the ops that calculate and apply gradients. Train op. MNIST.training. Oh, so this is going to call the actual... This is another hidden thing, which is annoying. Def training. Scalar summary. Oh, they save off some input. Right. So they're using gradient descent with the learning rate that you specified under flags.learning rate. And let's see, global step. What step you're on? No. Train op optimizer.minimize. Interesting. So normally I'm not used to seeing it like this, as optimizer.minimize. Usually just you evaluate a particular node on the graph. So interesting. Okay. And then you do eval correct. So you compute the predicted probabilities after training, of course. Anywhere your biggest probability is the correct label, you tick up 1. Summary op, build a summary operation based on TF collection. So you're doing some logging along the way. Create a saver for writing training checkpoints. You're saving your results at every step. And this creates, so that was all set up. Creating TensorFlow nodes to do what you want to do. Now we create the actual session. Then we initialize all those all those variables, like the weights. Then we create a node to initialize the weights. Then we actually run that node to actually initialize the weights. Summary writer is what actually saves off the information into trained-er. And what does it save off? Sesh.graph. Then after everything is built, start the training loop. So here's when you do some actual training. Now we're going to go through max steps. So distinct from how many steps are in a batch, which just says, we're just going to do this many steps. So we grab our data of the appropriate type. We do the training op and the loss op. So this is the fetch operation in TensorFlow. What do you want to get back? What do you want to put in? The feed dict, our data set. And so this gives us the training op, which we don't actually need the output from. That just computes weights. And the loss value, of course. And how long did it take? Hey, that's where that time.time came into play. Okay, every 100 steps. That's this. Percent is a modular arithmetic. So if I say 2 mod 10, that's just 2. But if I say 12 mod 10, that's also 2. You can sort of keep subtracting this number from this number until this number is smaller than this. Or I've heard of it taught in schools as like clockwise arithmetic. If it's 11 in the morning and then you add 2 hours later, what time is it? It's 1 o'clock, because we do time mod 12 or mod 24 if you're in the military. Yes. So every 100, you just get some information to your summary. You print out, hey, what's the current loss? Your loss should be going down. You save off this information using this data that it says, oh, what's the current data that we ran into? We add it. And flush is going to say, hey, actually write that to the file now. Don't just keep it in a buffer somewhere. In case something goes wrong, we want to make sure we actually write it now. Save a checkpoint and evaluate the model periodically. So every 1,000 steps. And at the end, save off our part of our model. We're saying +1 because we don't want to save at the very beginning. So it's not every 1,001 steps. It is every 1,000 steps after the first one. Right, so here's we check against the model. We say, all right, how many correct did we get against the training data set? How many correct did we get on the validation data set? Recall that's for building up your model. And how many correct did we get on the testing data set? So what is the final error of our model? And that is just about everything. We just make a stupid function, def main, that calls run training, which was that function we just had. And they have if name equals main, do this tf.app.run business. So if you just run this from the command line, that's what's going to happen. And actually, I'm just going to do %run fully connected feed.py, and it's going to run, yell at me. Learning rate, conflicting option string, -- learning rate. That's cute. Let me close that real quick. Let me make a nice clean data set there. I'd probably define learning rate at some point, and it wasn't happy about that. So if you don't want to work interactively, you can just do %run, and that will run a script. And now I notice every 100 steps, it's telling me what's going on. Every 1,000 steps, it's saving off some information. Loss is going down. And then it went, and now we're good. And you might be wondering, okay, well, how do I get at my model then? That is a good question. I endeavor to find that out right now. Maybe you can't. Globals. Function globals. What are my globals? So in IPython, you can ask for what variables are in the global scope. What are just sort of the regular variables that I have? Do eval, flags. So I think this is probably not a great example for understanding how to use TensorFlow interactively. This is this is a given script. You can just run this and get what you need. Main, mnist, placeholder inputs. Oh, see, oh, that's the function. Yeah, you don't want that. Ain't nobody want that. So, but that defined everything. What does run training do? Run training. Okay. So here's a thought. Rather than call this function run training, let's run our own. Let's just run these ourselves, shall we? I'm not going to do this in a special scope. I'm just going to do this straight up because I'm a terrible person, maybe? Well, maybe. Let's just run some of these real quick. We've got 5 minutes left. Plenty of time. Because this way we'll actually have the variables in our scope. Which is how I like to work, because I like to inspect everything that's going on. Alright, we initialize things. Do I have a session? What's sesh? Apparently I do. I didn't think I did have a session. Summary writer. I don't need a summary. That's not. I don't need that. That ain't me. Oh, jeez. I'm just going to do the actual training operation. There we go. Believe that's going to work okay. Ding. Okay. Duration. That's for the last. That's just the last op. The last step. Note that we did. 2,000 steps. Very nice. So you can look at loss value. What is my model now? How would I extract my weights from my model? I would need to get at those weights, but those are hidden inside this, not this fill feed dict. They're hidden inside mnis.inference. All right, so what's logits? Logits dot get shape. No. Right, because that's just 100 images, the final output probabilities. This doesn't show us the weights, inherent weights. But there is almost certainly a way to get at them. Yeah, I don't like obscuring my information with something like this. But not when I'm learning. If this is like a script I'm providing to someone else and say, hey, just run this, then yeah, sure, do what you're going to do. Can I use sesh.graph? Is that something you can do? Whoa, that's not something you can do. Sesh.seshString? What is that? Oh, well, there's nothing. Okay. Maybe there's not a good way to get at the weights here. Let us check the TensorFlow mechanics page. On Get Started. On Tutorials. No, back to Get Started. Maybe really interactive usage is just how the mechanics. There we go. Tutorials and this tutorial files fully feed connected. So this is how you can get to the page. The code to build a fully connected. The code to train a fully connected. Oh, so clearly I just sort of walked through mnis.py. Prepare the data. Right, and they walk through this in a little bit more detail. Loss, training, graph, the session, train loop, feed the graph. The graph is hungry. Visualize the status. Tensor board. Yeah, well. All right, you know what? I will attempt to run tensor board, perhaps. Click to try tensor board with data from this tutorial. Sure. Oh, no. I wanted to run it myself, buddy. No. Running on your website doesn't help me. If I can't run it myself, it's not going to help. Launching tensor board. There we go. Proj/TensorFlow. CD data, I guess. Yeah, events.something. So logder is right here. This is where the logged events have been logged. Let's see if tensor board works now. It's been a long time since I tried it. You can navigate to here. All right, sure. It says IO error. No such file or directory. That's interesting. Let's see if that actually works. Probably not. Tensor board starts up. Images, graph, histograms, events, tensor board, question mark. Tensor board. Path to logs. Alright, let's see, what was the path to logs? Summary writer. Flags.traineder. Yeah, that's definitely it. Right. But I don't have no such file or directory. TensorFlow, tensor board tag, apparently. So maybe I'm missing something from my tensor board still. Unable to read tensor board tag. Interesting. Alright, so tensor board still has some trouble. Maybe I'll get to that at another point. I tried. For more details, see this tutorial. All right, whatever. But we walked through line by line, as advertised, the fully feed connected tutorial here, which might be okay for getting a feeling for how they read in data. This mnis.py is really the key of how they're specifying their model right here. Maybe I'll walk through something like that in the future. I personally love to work interactively, so that's how I'm definitely gonna approach things in the future. And like here, they actually go through and it's like, oh, you define the weights, you define the biases, you define the neural network. A lot of the trouble of neural nets is, or of any data science problem, is reading the data. So I do appreciate the thorough walkthrough of this is what this data is, this is how you actually get to it. But I wouldn't have liked to see this sort of, not skipped over, but I would have liked to see this more prominently. Because like this is sort of the fun part. So we shouldn't just skip over the fun part, right? All right, but that was line by line. I hope that wasn't hideously boring. If it was, let me know, and I'll do fewer of these. If that was helpful and it walked through things and it was good, let me know that too. And you can tell me on YouTube, on Twitter, on Reddit. Oh, did I forget to submit the post? I did. Tell me on Reddit as I submit the post now. Way too late. Upvote, downvote, whatever kind of votes you like. All right, you guys have a good night.